Hi folks, today we are going to look at a front panel from a Sony model FH-B510. For this project, we will spend a little more time examining the processor itself, while giving the panel only the attention required to get it running. As usual, I will explain the necessary power connections and indicate where each voltage should be applied. These instructions can also be useful for other similar panels, since there are roughly half a dozen variations of this model family. The only requirement is to confirm the connector pin assignments, as these may vary slightly from one version to another. As I often mention, one of the easiest ways to identify the presence of a real-time clock on a panel is to look for a 32.768 kHz crystal. Its presence is usually a very strong indication that the system includes clock functions. In this case, bringing the panel back to life is particularly interesting because of those built-in clock features. The procedures for setting the clock and configuring the timers are straightforward and are fully described in the original user manual. For those with a particular interest in audio electronics, there is another feature worth highlighting. The panel includes a 5-band audio equalizer circuit, based on two integrated circuits with the reference M5226FP. To make use of this section, we must provide plus 7.5 volts DC, minus 7.5 volts DC, and the corresponding analog ground reference available through connector CN502. With those supplies present, the equalizer can be reused as part of a custom audio project. All of the display animations and keyboard interactions are controlled by a device from NEC reference uPD78042GF. This component belongs to a family of devices that combine an 8-bit microprocessor with an integrated VFD driver. This combination made them very popular in consumer electronics of the period. The main limitation of these devices is that they belong to the OTP family, meaning one-time programmable. In other words, the firmware stored in the original memory can only be programmed once. Once written at the factory, it cannot be modified. As a result, we cannot alter the original software contained inside the device. Even so, this family of NEC processors is still very interesting to study. Although this particular version uses an internal PROM, making modification impossible, there are other members of the same family that use flash memory instead. Those versions can be identified quite easily. They include the letter F in their part number. For example, references such as uPD78FXX indicate a flash-based version. Unlike the OTP models, those devices can be reprogrammed. To modify them, we would need the appropriate development tools. These are generally similar to the tools shown in the NEC documentation. Typically, this includes a universal programmer, an OTP programmer, and the appropriate socket adapters. Although the original C compiler for these devices is not readily available today, programming them is still possible using assembly language. The instruction set and mnemonics are documented in the datasheet for the uPD78042GF, making low-level development entirely feasible. Of course, that assumes access to the required programming hardware. Now let us move on to the power supply arrangement used to bring the panel back to life. For this project, we used three completely independent power sources. The first supply provides plus 5 volts DC to the filament through a 1N4004 diode. The second supply provides plus 5 DC for the logic circuitry. The third supply provides minus 29 volts DC. This negative voltage was obtained by connecting two DC to DC converters in series, a B0505S and a B0524S. Once these three supplies are connected correctly, the panel operates exactly as intended. With relatively little effort, we can once again enjoy the display animations, clock functions, keyboard interaction, and even the audio-related features that made these systems so appealing when they were originally released.